now let's tackle ethane. So ethane has a chemical formula that looks like this. CH2H6, like that. You could also represent it like this. That's one way to do it. And then expanding it out, we would see it represented in its tetrahedral geometry a little bit better. How do I know it's going to be a tetrahedral geometry? Well, because when I look at this carbon, I can see that there's 4 electron groups around it. So if I expand it out, hydrogen, 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 like that, then I could expand those out, like so. And how could I represent that with zigzag structures? I could represent it with just a line, because that line represents this, right? And now we're back to where we started. So in short, how do I know that's sp3 hybridized? Because that carbon that I'm pointing to with the green arrow has 1, 2, 3, 4. So that has to be sp3 hybridized. And an sp3 hybridized carbon is going to have a tetrahedral geometry. Now, what would that look like then? Okay. Well, if we go back to methane, we had a carbon. We know that 2 of the bonds in a tetrahedral shape has to be in the same plane with a bond angle of 109.5 degrees. And then you would add in your wedge and your dash like that. So that's exactly what we're going to do here with our ethane molecule. We already have this carbon-carbon bond in the plane because I've drawn it with just a line. I haven't drawn it with a wedge or a dash. And so we would just then put our hydrogen. So this hydrogen could be that hydrogen. And then this one could be a dashed hydrogen. And this one could be our wedged hydrogen. So now do you see the analogy here? Boom, boom. It's the same thing here. Like that. And then we have our wedge and our dash. Wedge and our dash. Okay. So now we have another carbon. Okay. And I believe the way that the software has drawn it, it actually puts the hydrogen, this hydrogen in the plane there, and then it dashed this way, and the wedge like that. Okay. So you guys will learn shortly that there's free bond rotation around here, and you could have the molecule look exactly like this if you wanted to. It could have been drawn like this. And the way I'm drawing it now is what's called a conformation. It's just a different conformation, but it's still the same molecule. So this molecule here and this molecule here are the exact same thing. It's just they're being represented in a different conformation because you can rotate around a carbon-carbon single bond. Okay, so now let's go to the software so you can get a better view of what's going on here. So if we draw ourselves ethane here, we have a carbon, carbon, and if I draw it Lewis style, I would just draw in the 3 hydrogens like this really, really quick. And then the software is going to interpret that as the way I've drawn it here with the wedges and the dashes. Okay. But if we want to draw the wedges and the dashes, we could do that as well. So we could switch that to a dash, that to a dash, and then this to a wedge, and that to a wedge. Okay. And you can see the molecule on the right, it didn't change anything. So when we take a look at this, okay, and you can view it in all different types of angles, Okay. But when you focus just on one of the carbons, this one right here, okay, orient it that way. There we go. That looks a little bit better. Oh, this is a finicky program. I try my best here. There we go. Okay. So that carbon right there, I want you guys to see that this hydrogen and that carbon, let's get it oriented right. There we go. So this hydrogen here, this carbon here, and then the carbon-carbon bond right there. Can you see that the bond angle is 109.5 between those right there? And so what I'm trying to show you is the bond angle from here to there in the program. Okay? So we just, it's really good to be able to visualize these molecules. Okay? And model kits really help with that. Okay, so let's get back to what we're really here for, is what orbitals are used to make this molecule here. So let's use this one up here. Okay. Okay, let's see. Skipping ahead, we have, let's call this the red carbon here. Okay, and then we'll do a blue carbon here. Okay, so for the red carbon, we're going to hybridize it to sp3. So that means sp3. How many valence electrons comes with that red carbon? 4 of them. And then we have the blue carbon. That is also sp3 hybridized. So that's going to come with 4 valence electrons right there. And then we have, in yellow, our hydrogen atoms. And they come with a 1s orbital with 1 electron each, and there are 6 hydrogens. So times 3. So now that so how we represent these bonds now, let's draw our 2 carbons right next to each other. Okay. The red carbon is going to come with sp3 hybridized orbitals. We're going to have one here, there. This one is at the wedge, and this one would be our dash. And then our blue carbon is also going to come with sp3 hybridized orbitals. So this bond right here, I'll draw it here. The wedge, I will draw it here. And they should all be, these orbitals that I'm drawing should all be the same size. It's just I'm not a good artist. And then that dash bond would be right there. And then this bond right here, this right here, is going to be represented like this. And you can see that this carbon-carbon bond right there is a covalent bond. And when you look at the atomic orbitals, there's head-to-head orbital overlap right there. And so that would be a sigma bond. So we would say this bond right there is a sigma bond. This orbital overlap is sigma. Okay. And so let's see if I can get rid of the shading. Nope. That's going to be a little bit more difficult. Okay, I'll just leave the highlight there. Remember that for the red carbon, it's coming with 4 electrons. So let's draw those in. Okay. And then the blue carbon is coming in with 4 electrons. So let's draw those in. Now, that pink overlap, or that sigma bond between the carbon-carbon, you can see that it's 2 orbitals, the red one and the blue one, head-to-head overlap, interacting in a constructive interference, giving us our bond. Now we have hydrogens. And so what I'm going to do is kind of keep track of the electrons here. So those two right there is this one and that one. Okay? Now we are going to bring in our hydrogen atoms. There's our hydrogen atom, and it comes with 1 electron. So we've used this one, and now we're down to 5. And if I bring in another hydrogen, got rid of this one, now we're down to 4. And all the way around, you can see that I'm just keeping track of all the electrons and where they're at. This one, boom, down to 2. This one, down to 1. And then our very last one, like this. And those also, we have head-to-head orbital overlap, making those bonds, or those interactions, sigma as well. So those are sigma. So this is sigma. So all the bonds in ethane are sigma bonds. They're all covalent bonds because we're sharing electrons. And so I could ask you, if we were looking at this molecule then, let's take a look. If I asked you, describe for me the orbitals used for that sigma bond, you would say, well, that's easy. I know that this carbon here is sp3 hybridized, and it's forming a sigma bond with a hydrogen atom, and that comes with a 1s orbital, like that. Now if I asked you, well, what about this sigma bond right there? What orbitals are used to form that bond? Well, you can see that this carbon right here is sp3 hybridized. This carbon on the right is also sp3 hybridized. So this bond right here that I'm highlighting in orange is formed because you have an orbital overlap on 2 different carbons, but that orbital overlap is right there. And those 2 orbitals that we're using to form that sigma bond are sp3 hybridized orbitals. Okay. So that's how you would draw the atomic orbitals in ethane.